material and engineering mechanics, they'll get balanced. They'll get balanced. And coming to the mechanical engineering, gate point of view, it is around 7 to 9 marks. It is also good weightage for mechanical engineering. So after engineering mechanics, this is the next fundamental subjects. Most of the interview questions will also come from this subject. So this is giving you the basics of the machine design and theory of machines. And for civil people, the strength of material gives you the basics of structural analysis, RCC, steel and pre-stress concrete. All the design subjects are related to this strength of material subject. And the syllabus is concerned, syllabus for civil engineering. If you look at the syllabus at a broader view, this is the gate syllabus given by the gate people. The bending moment and shear force in statically determinate beams. Statically determinate beams are covered in strength of material, indeterminate beams are covered in structural analysis. So, in our strength of material, we will be covering determinate structures like simply supported beams and cantilever beams, maybe overhang on one side, overhang on two sides. That is our limitation. So, simply supported, single overhang, double overhang, cantilever beams are in our strength of material syllabus. And compulsory from this area, there may be chance of 2 marks question. So, concentrate on bending moment and shear force diagrams. No need to draw the complete diagram for the analysis point of view. If you can able to calculate reactions properly in a beam by using the equilibrium equations, and if you can able to find out bending moment at a section and shear force at a section of a beam, that is more than enough to get 2 marks. And with a little fundamentals are enough for this 2 marks. So, if you have good practice on simple things, getting 2 marks is easy. So, don't ignore this area. Coming to the other things, simple stresses and strains and relationships, chance of 2 marks here. Whatever is written in blue, simple stress, strain and relation between the stresses and strains through elastic constants. So, chance of 1 to 2 marks, 1 to 2 marks here. There may be chance of 1 mark. If 1 mark question is coming, no chance of 2 marks question. Usually 1 mark or 2 marks, but SFD BMD there is a chance of 2 marks directly. Coming to the next things, whatever is given in green, all related to the beams, simple bending theory, flexural and shear stresses and shear center. So, from this area again there is a scope of 1 to 2 marks. Bending stress, shear stress and shear center. Simple area where there is a scope of 1 to 2 marks. Same as simple stresses and strains. Next, uniform torsion. Uniform torsion. Be careful, this is uniform torsion. Uniform torsion means same torsion is there throughout the shaft. Variable torsions are not there in our syllabus. So, uniform torsion, even mechanical point of view also uniform torsion, that means torsion should be uniform throughout the cross section. Chance of maximum 2 marks, that means 0 to 2 marks you can say. Mechanical point of view torsion is important, civil point of view bending, shear are important, because most of the shafts while transmitting power, they will be subjected to torsion, but most of the beams and columns subjected to bending or buckling will be subjected to bending moment plus shear. Next is stress transformation, nothing but stresses on inclined planes, principal stresses, nothing but complex stresses. Complex stresses will have 2 marks, chance of 2 marks from complex stresses. Next is the combined direct and bending stresses. Combined direct and bending stresses, chance of 1 to 2 marks. Combined direct and bending stresses, nothing but columns subjected to eccentric loading. Direct stress plus bending stress. Direct stress means coming from the simple stresses, and bending stress will be coming from the theory of pure bending. So 1 to 2 marks. So these are the areas where you need to concentrate. Even if you concentrate on very fundamental things, you can target 70 to 80% of the questions which are coming from this area. Around 70% of the questions are easy to moderate level questions from these areas. We will target those areas, and remaining 20% questions are extraordinary questions, maybe critical questions. If luck is there, you can solve those questions also with minimum preparation. With this quick revision classes, you should be in a position to get 60 to 70% of the questions from simple revision through this quick bite. So 2 marks here, 1 to 2 marks, 1 to 2 marks, maximum 2 marks means 0 to 2 marks. Next, stress transformation 2 marks, and combined and direct bending stresses, you can say 1 to 2 marks. This is for civil engineering point of view. Coming to the mechanical syllabus, look at the mechanical syllabus. Seems to be lengthy, but actually it is slightly less syllabus compared to the civil people. Almost the questions of civil engineering will sometimes reflect in mechanical engineering gate, and sometimes mechanical engineering gate questions will reflect with slight changes in civil engineering also. That is why the people who are preparing civil engineering gate should solve the PYQs, previous year questions of mechanical also, and vice versa. Mechanical people should solve the gate previous year questions, so that some questions are getting interchanged in most of the areas. So keep this point in your mind. What you need to do is, if you have friends of civil or mechanical, say suppose if you are mechanical student, take civil PYQ booklet and tear off the strength of material, fluid mechanics and mathematics questions, and you solve them. And if you are civil person, take the PYQ of mechanical friend booklet, take out the same strength of material, fluid mechanics and then mathematics. Then you can try to solve them for the exam. There may be chance of repetition, or similar questions may reflect in your GATE 2025. Keep this point in your mind, especially strength of material, fluid mechanics and then mathematics. Mechanics, engineering mechanics questions, and civil people will have only statics. Mechanical people, they will get questions concentrated on dynamics. It is a completely different story. Coming to the first chapter, simple stresses and strains, elastic constants and Poisson's ratio. Nothing but simple stresses chapter. There may be chance of 1 to 2 marks from this area. 1 to 2 marks, simple stresses, strains, elastic constants, nothing but a relation between stress and strains with Poisson's ratio. Next is Mohr circle for plane stress and plane strain system. Plane stress nothing but 2D stress system. Mohr circle for plane stress and plane strain is nothing but complex stresses. Important for your machine design, theory of machines also. 1 to 2 marks. No need to draw the Mohr circle. If you have the fundamentals of the Mohr circle, that is more than enough. And for civil people, they have given only stress transformation. Stress transformation can be done through the Mohr circle. So civil people should also have the knowledge on the Mohr circle and stresses on inclined plane, principal stresses and all. The same is required for the mechanical people also. For plane system, plane stress and plane strain system means 2D system they are asking you, and in machine design you may go for the 3D system, 3D cases, 3D state of stress at a point will be discussed in your machine design. Now thin cylinders is given in mechanical syllabus, only thin cylinders. For civil people also in syllabus they have not mentioned thin cylinders, but questions are coming occasionally in thin cylinders. So you also need to have very minute understanding of thin cylinders. Only just if you remember what is thin hoop stress and what is longitudinal stress developing in a thin cylinder, more than enough. So for mechanical people, as it is mentioned, you also get the same type of questions from thin cylinders. Very thin questions will come. So I can't guarantee a question, a mark in the question from the thin cylinders. So I am not writing anything for that. Next is another important area for mechanical and civil also, the shear force and bending moment diagrams for determinate beams only. For indeterminate beams, it is only for civil people, for mechanical people it is not required. So in this area there is a scope of 1 to 2 marks, SFD and BMD. Again for SFD, BMD you should be in a position to calculate reactions for a beam that you might have come across engineering mechanics by using the equilibrium equations, and then we need to calculate shear force at a place and bending moment at a place. That is more than enough for your analysis point of view. Next set of questions will be from bending and shear stresses, the concept of shear center. Same thing is there for civil people also. Bending stresses, shear stresses and shear center. Previously shear center was not there for mechanical people. Now it is included just to identify where would be the shear center for different sections is more than enough for civil as well mechanical people. Nobody will ask you to analyze and nobody will ask you to calculate the shear center location exactly. Next, deflection of beams, statically determinate beams are given in our syllabus. Slopes and deflections. Deflections are mentioned, they may ask you slope also. Next, torsion and circular shaft. Torsion is important for mechanical people. From bending stresses, shear stresses and shear center, there is a scope of 1 to 2 marks. Torsion and circular shafts is important area for mechanical people. For your machine design, this is having good score. So up to 2 marks you will get it. Chance of 2 marks question from torsion. Euler's theory of columns. You see, only you have Euler's theory in your syllabus, which is applicable for long columns which fails by buckling. Chance of 1 to 2 marks. Only Euler's theory, either 1 mark question or by mistake 2 marks question is coming. Rarely it comes. 2 marks question is very rare, but usually there is scope of getting 1 mark question from long columns based upon the Euler's theory. Energy methods are important, especially to find out the deflection by energy method is important for us. So energy methods, scope of 2 marks directly. Energy methods to find out, strain energy method to find out deflection. Next, the thermal stresses are separately mentioned. That's why most of the questions from the simple stresses chapter will be related to thermal area. So mechanical people should concentrate on the thermal stresses, which is a subset of first chapter, stresses and strains, which is included in the first chapter. Actually, it is mentioned separately. Next is all theory question. One theory question may come from the remaining area. 1 mark question may come mostly from strain gauges and rosettes, testing material with universal testing machine, testing of hardness and impact strength. And this theory is not specially mentioned to civil people, but they also have the same syllabus. You may get 1 mark out of this complete theory. Strain gauges, strain rosettes, testing of the materials, especially the tension test on various material, compression test and all. Universal testing machine with UTM, the tension test is commonly done. Testing of hardness and impact. These are all the material properties are commonly required for mechanical people, and it is also important to some extent for the civil people. So, important areas, the first chapter 1 to 2 marks, stress strain and elastic constants, Poisson's ratio along with the temperature stresses may be 1 to 2 marks. Next is the complex stresses, Mohr circle and stresses on inclined plane and principal stresses 1 to 2 marks. Bending stress, shear stress and shear center, rarely shear center question may come for mechanical people. Till now no question, in future it may come, that may be for 1 to 2 marks. Deflection of beams is important. Either you can use any one of the methods, you can use it, either double integration method or conjugate beam method or strain energy method. For mechanical people or civil people, it is better to use conjugate beam method or strain energy method. Next is the Euler's theory of columns. Hardly one question will come, 1 mark question may come. Thin cylinder also a very thin chance of getting 1 question. Remaining theory, material testing, may be chance of 1 mark. If at all a person is very much interested, they may give you a theory question on 2 marks, but that is a rare issue. So, with this introduction, we will enter into the first chapter, stresses, strains, elastic constants and Poisson's ratio. Okay. So, nobody will ask you definitions, but they will ask you questions based upon the definitions. 90% of the questions in GATE exam are numerical based, remaining 10% of the questions are theory based. Theory, very less chances are there to get a theory question in GATE exam, especially in our strength of material, except the theory area where you use testing of the materials. Now, coming to the stress is resisting force per unit area, strain is change in dimension upon original dimension. And just before we go for the other things, we will talk about few assumptions in strength of material. In our assumptions, first assumption is we assume that material is homogeneous and isotropic. Material is homogeneous and isotropic. Homogeneous means it is having uniform composition throughout the material. Uniform composition means it should be coming from a single metal or single material. It should not be the mix. So, uniform composition is nothing but homogeneous. Isotropic means at any point in all the directions you have same properties. At any point in any direction you consider, if the properties are same, we call it as isotropic. So, throughout our strength of material, not only strength of material, in all our designs, whether it is civil design or mechanical design, we consider homogeneous plus isotropic. Same composition of material we use it throughout, and same properties in all directions at a point. Second is initially we ignore the self weight. Self weight is ignored. Very important case is superposition principle is valid. Except for strain energy, superposition is valid everywhere. Superposition means adding the things to get the final effect is called superposition. If you have 3-4 loads on a beam, no need to consider all the loads and analyze at once. You can consider a beam with each and every load separately, you can analyze, and finally algebraic sum of various effects is equal to the resultant effect. That is called superposition principle, and superposition principle is valid for if deflections are very small. If deflections are very small, we can use superposition. For a member with large deformations and deflections, you can't use superposition principle. And this superposition is not valid for strain energy, not valid for deep beams. Why it is not applicable to strain energy, we will discuss later on. It is not applicable to deep beams. Okay. Next is sudden variation of cross section is not allowed. We consider prismatic members. We consider whether beam, column, shaft, we will consider it as prismatic only. If it is non-prismatic, sudden change in cross section may cause stress concentration. As per St. Venant's theory, sudden change in any cross section or any profile of the cross section will cause stress concentration. To avoid the stress concentration, we will take all our members are prismatic. So, these are the things we will consider before we proceed into the strength of material. Next is stress strain curves are important for objective question, 1 mark question, and usually the stress strain curves based on the tension test on mild steel bar they may ask you. So, first we will talk about, just we will touch stress strain curve of mild steel. Mild steel is nothing but ductile steel, low carbon steel, it is very soft steel. In stress strain curve of mild steel, you come across so many variations. That is why the stress strain curve of mild steel is very commonly asked. Usually the strain is an independent parameter, that is why we use it on x axis. The stress is a dependent parameter, we will use it on the y axis. In any graph, independent parameter is shown on the x axis, dependent parameter is shown on y axis. So, if you test a mild steel bar in UTM, the stress strain curve will be like this. This is nominal stress and nominal strain. Nominal stress is nothing but resisting force per initial cross sectional area, and nominal strain is nothing but change in length at present divided by the initial length. Change in dimension upon initial dimension is original strain definition. Presently in tension testing on a mild steel bar in UTM, we will consider the dimension as a length. So, strain is change in length upon initial length. Before you start the experiment, what may be the original length of the member, original gauge length of the member, we need to use it for the strain. Even while calculating the stress initial cross sectional area, before you start the experiment, we use it as the initial area for the calculation of nominal stress. Now, the stress strain curve is starting from origin because the self-weight is ignored. Once self-weight is ignored, stress is 0, strain is 0 by the time you start the experiment. So, we ignore self-weights to make all our graphs starting from origin. And there will be a point A called proportionality limit. Up to proportionality limit, the stress is proportional to strain. Hooke's law is valid. If you apply the load, member deforms, and remove the load, it comes back to original shape and size immediately, instantaneously. The graph is straight. That is why we call it as linear elastic also. And after that beam, the member may be elastic, but may be non-linear elastic condition. So, up to point B, the material is elastic. That's why point B is called elastic limit. Up to point B, material is elastic. That means if you apply the load, deforms, remove the load, it will come back to the original shape and size by the same graph up to the point B. Immediately after point B, the yield occurs. Yield means permanent deformation starts in the material. So, the permanent deformation starts at point C is called upper yielding point, and that start of the yield will be with a jerk. So, that jerk gives you reduction of the strength of the material from C to D. So, C is called upper yield point, D is called lower yield point. Upper yield point, D is called lower yield point. The permanent deformation starts at C. That starting of yielding is by a jerk. That is because of the slip, sudden slip of the molecules, sudden slip between the molecules of the material. And after that there is a horizontal plateau, almost horizontal line DE, with slight jerks may be there. If you observe this DE very closely, there may be slight ups and downs. So, that DE is called plastic zone, where permanent deformation comes at a constant lower yielding point stress. That is why for all calculations, the yield strength of the material is corresponding to the stress corresponding to the lower yielding point Fy. Yield strength of mild steel, if you say 250 megapascal, that is corresponding to the stress at a lower yielding point. Okay. And after that the graph is going up and reaching to F. So, point F we call it as ultimate point. The stress corresponding to ultimate point is ultimate stress. After that neck formation comes and graph comes down and fails at point G. G is called breaking point. Try to remember various points on the graph. So, the stress corresponding to ultimate point is called ultimate stress. The stress corresponding to breaking point is called breaking stress. Ultimate stress and breaking stress. So, this is Fu, this is Fb. So, we never use ultimate stress and breaking stress in general designs. For general designs we use only the yield strength, which is corresponding to the lower yielding point. There are various zones in the stress strain curve. OA is a linear elastic zone, where Hooke's law is valid. AB is a non-linear elastic zone, where material is elastic but Hooke's law is not valid there. B and C almost coincides, points B and C almost coincides. CD is yield zone, where slip of the molecules comes into the picture. Next, DE is the plastic zone, where permanent deformation comes at a constant stress. EF is called strain hardening zone, FG is called neck zone. EF is strain hardening zone. FG is called strain softening zone, otherwise neck formation occurs, necking zone. This is based upon the nominal stress strain curve. If you want a true stress strain curve based upon the true or incident area, there may be slight variation in the curve. So, this curve will go like this, like this, like this, and slightly goes up and then fails. The blue color is the true stress strain curve. White line is nominal stress strain curve. True stress strain curve is based upon the instantaneous area. For calculation of the stress we use. For calculation of strain, we integrate the change in length by original length from initial position to final position. Incremental increase we will consider for calculation of true strain. Okay, in case of true stress strain curve, it goes up and then fails. So, it fails at G dash. Okay, it fails at G dash, not at G. The neck formation in nominal stress strain curve is indicated by the sloping down curve from point F to G. There are some idealized curves which are generally used in designs. Those idealized curves are important for 1 mark. We will just touch idealized stress strain curves, important cases. Idealized nominal stress strain curves only, based upon the nominal area. So, in all the cases we are using the strain on x axis, stress on y axis. If the graph is passing through the origin and it is a straight line, we call it as linear elastic. Linear elastic stress strain curve. And if the stress strain curve is flat and horizontal, we call it as pure plastic stress strain curve, ideal plastic. Ideal plastic stress strain curve. Otherwise, if you have stress strain curve passing through the y axis, we call it as rigid, perfectly rigid. Rigid body will have stress strain curve parallel to y axis. And if you have stress strain curve coinciding with the x axis, we call it as ideal fluid. Ideal fluid will have complete deformation at zero stress. So, ideal plastic may also call it as, so rigid in the initial stages and then horizontal line. So, you may also call it a rigid plastic. Rigid plastic or ideal plastic, both are the same. Depends upon the options available in our multiple choice questions, you need to pick up the answer. Next is any graph like this. This is called elastoplastic or otherwise linear elastic and then plastic. Elastoplastic stress strain curve. We also call it as linear elastic and then plastic. First part is linear elastic, then horizontal line is the plastic stress strain curve. Next is if you have the graph like this, inclined straight line not passing through the origin, we may also call it as first part is rigid and then strain hardening. Rigid strain hardening. If the graph is sloping down in the initial stages, you may call it as rigid and then strain softening. Initial portion is rigid and coming down is called strain softening or necking. Rigid strain softening. Strain softening is also called as neck formation. So, there may be chance of different combinations of this idealized curves, important for 1 mark, try to remember this. The change in length of a member, deformation due to axial force, change in length or change in dimension due to axial force is given by, say suppose this is a member, you apply a force P, the change in length is given by PL by AE. This you remember for homogeneous prismatic members. Here P is applied force, L is length of the member, A is cross sectional area, E is Young's modulus. AE is called, what is the name of AE? You remember? What is that? Axial rigidity. And some people call it as AE by L, nothing but delta L by P by delta L. Force required to cause unit deformation. Force required to cause unit deformation. P by delta L, I am taking here AE by L, is equal to axial stiffness. Axial stiffness is the force required to cause unit change in length of the member. Force required to cause unit change in length of the member, which can be calculated as AE by L. If the member is having non-uniform cross section, say non-prismatic cross sections, maybe tapering bar like this, the bar diameter is changing from small d to capital D, it is subjected to axial force. You can't use PL by AE for this member. So for this member to calculate change in length, PL by pi by 4 capital D into small d into Young's modulus. Try to remember it, actually you need to integrate to find out this. So if you simplify, it is 4 PL by pi E capital D and small d. This is for tapering circular bar, because these cases may come directly in our objectives, be careful about it. If you have a square cross section tapering from A into A to B into B, a square cross section like this. Square cross section, you have the cross section A into A here, changing to B into B. In this case, the change in length is given by PL upon AE, directly you can't use it. So I am modifying it as PL by small a on one side, small b on one side into Young's modulus. By heart this may be useful for you directly in our objectives. Next is in case of stepped bars. Stepped bars means you have different cross sections attached together, maybe different forces acting at different junctions. In this case, what do you need to do is, you need to use free body diagrams to analyze these members. Maybe here P3. You need to take the free body diagram to analyze these members. So if you take the three parts, each and every part is prismatic now. So total change in length is equal to change in length of first part plus change in length of second part plus change in length of third part. For each and every free body diagram, you can use PL by AE for calculation of the change in length. So to get the free body diagram concept is very simple. You can separate, free body is nothing but a separated body which shows actions plus reactions. Actions and reactions are to balance the member. So this is part 1, this is part 2, not to the scale, this is a part 3, not to the scale. So part 1, part 2, part 3. If you want force acting on any part, what do you need to do is, you need to keep your hand in the middle of a part and either you see left side or right side. Either you see the net force acting on the left side or right side, whichever is easier, wherever you have less forces, that is better for you. So if you want free body of part 1, keep your hand in the middle of part 1, look left side, left is better because only one force P4 is there. And if you want to look at the right side, you need to consider all P1, P2, P3 together. But however, the total member is under equilibrium means the left side forces must be equal to right side forces. So to make a simple free body of part 1, look at the left side of part 1, we have P4. So keep it like this and balance from the other side P4. Now this is under equilibrium. Now coming to P2, keep your hand in the middle, either you look left side or right side. If you look at the left side, it is P4 going to the left side, P3 coming to the member. So P4 minus P3 is the net force acting on this member. If you look at the left side, P4 minus P3. P4 minus P3. P4 is acting away from the member. I have shown away from the member as positive, towards the member automatically becomes negative. To balance on the other side, it is P4 minus P3. Okay. In the same way, you can consider this same free body can be taken by the other way also. So this is part 2. What I do is I keep my hand in the middle of the part 2, look right side. Right side means P1 is acting away from the member, P2 also acting away from the member. So if you look at the right side, it is P1 plus P2, both are in the same direction. To balance on the other side, P1 plus P2, either you consider this case or this case, both are the same. Any one, whichever is easier for you, that you can consider. Now coming to part 3, looking at the right is better because there is only one force right of the part 3. What is the force acting on right of the part 3? P1 only away from the member. So P1, to balance it on the other side also P1. So like that we will take the net forces acting on different members through free body diagram. Once you have the free body diagram, calculating change in length is easier for us. We will take one example on this basis. Say I have a member like this. It may be each and every part is prismatic by nature. The forces acting on this will be 30 kilonewton, 20 kilonewton, this is force P, $80 kilonewton. The data is given part 1, part 2, part 3. Axial stiffness values are given to us. Axial stiffness is nothing but AE by L. AE by L is nothing but force required to cause unit deformation. So this is part 1 is 10 kilonewton per meter. Part 1. Part 2 is having 20 kilonewton per meter. Part 3 is having 15 kilonewton per meter. Calculate total change in length. Like this questions may come in GATE exam. You should be, it may be a 2 marks question, you should be in a position to answer such questions in 2 marks questions means 3.6 minutes of time will be available for you to answer such questions. For 1 mark in GATE exam, you may have 1.8 minutes of time. For 2 marks question, 3.6 minutes of time is available for you. Okay. So first what you need to do is you need to do the free body diagrams. Try to solve the question. Let us see how many of you give me the answer. Your answers are not accessible to me, but we'll check up the answers at once at the end. Part 1, without knowing this force P, you can take the free bodies. So total member should be under equilibrium. You can calculate P, unknown force P, by using sigma Fx equal to 0, but without that also you can take the free bodies. Let us see how to take the free body without taking the value of P. All the 3 parts I am not drawing with scale, these are all without scales only. Part 1, part 2, part 3. To find out the force acting on part 1, keep your hand in the middle of part 1, look left side. Left side is 80 going away from member. Show the same force 80 going away from the member. To balance on the other side, 80 going away from the member, 80 kilonewton. For the next part, keep your hand in the middle, look left. If you look left side, 80 minus P is there, P is unknown. So better, instead of looking left side, look at the right side. If you look at the right side, 30 and 20 both are going in the same direction. 30 and 20 both are going in the same direction. So you put 30 plus 20 means 50 on the middle part. To balance, 50 is required on the other side, so that the member is under equilibrium. Coming to the part 3, look at the right side. What is the force? 30. You can look at the left side also, but left side unknown force P is also there, and so many forces may confuse us. Whichever is easier for us, that side is better to see. 30 away from the member. To balance 30, on the other side also make 30 kilonewton. Be careful with units. Now the total change in length is given by change in length of part 1 plus change in length of part 2 plus change in length of part 3. The axial stiffness AE by L values are given to us. So this can be PL by AE of part 1, PL by AE of part 2, PL by AE of part 3. So what is the force acting on part 1? Tensile force will take positive, compressive will take negative, but luckily all the members 1 to 3 are having tensile force only. Tension is causing elongation, compression is causing contraction. So the force acting on the part 1 is 80 kilonewton. 80 kilonewton. What is AE by L? 10 kilonewton per meter. AE by L is 10. So 80 kilonewton by 10 kilonewton per meter. So finally the answer will come in meter. For part 2, the force is 50 kilonewton, and what is its AE by L? Part 2, 20. So 50 by 20. For part 3, force is 30, tensile force. So 30, what is its AE by L? For part 3 it is 15. You can simplify and give me the final answer, it may come in meter. 80 by 10 is 8 plus 5 by 2 is 2.5 plus 30 by 15 is 2. Eight plus 2.5, 12.5. What I do is I will take the axial stiffness values as 10 kilonewton per mm, per mm, per mm. I am changing the units. Don't change the units like this in exam hall, but for convenience I am changing the unit. So finally the 12.5 mm is elongation of the bar. If you take a kilonewton per meter, the answer will come in 12.5 meter. So understand this. This is the way we need to calculate the change in length of the bar in total. This type of questions are very common in GATE exam, which comes for 2 marks. If time permits, try this question please. A circular bar is there and here it is a tapering member. $30 kilonewton, $80 kilonewton, $20 kilonewton. So both are having length 1 meter, having length 1 meter. Here the diameter is 30 mm dia. Here diameter is 10 mm dia. Young's modulus throughout is, calculate change in length. Total change in length. Take Young's modulus as 200 gigapascal. Making the free body is important. So try to solve this question. First take the free bodies. For prismatic member, PL by AE will be the change in length. For this tapering bar, you need to use PL by pi by 4 capital D into small d into Young's modulus. So Young's modulus, if you want, you can change into Newton per mm square. So 200 gigapascal is 200 into 10 cube megapascal, nothing but Newton per mm square. This is a common conversion, you need to remember it. They will give you in gigapascal, we need to convert into megapascal by multiplying with 10 power 3. Megapascal is Newton per mm square. So take the free body diagrams. Upper bar is prismatic. For prismatic member, not to the scale I am showing. What is the force acting on the first upper part? Either you look up or down, it should be the same. This is 50 please. It is not under equilibrium, this must be 50. 120. Otherwise, it may not be under balanced condition. Right. 111. Okay, 110. It is under balanced condition. So what is the force acting on the part 1? Either look up or down. Up, if you see, 30 kilonewton upside. Even if you look down, the net force should be 80 up, 110 down. So 110 minus 80 is 30 again. No need to balance it like this. Either you look up or down and decide it. And check up whether this is under equilibrium or not. That means sigma vertical forces must be equal to 0. So downward force is 110, total upward force is 80 plus 30 is 110. Everything should be under equilibrium, otherwise we can't balance the member. Next is the lower portion is having a tapering section not to the scale. What is the force acting on this tapering section? look down. It is 80 kilonewton acting upwards. So, 80 kilonewton acting upwards. To balance on the other side, 80 kilonewton should act downwards. Okay. Even if you look at the upper side of the lower part, what is the net force acting? 30 away from the member, 110 towards the member. So, 110 minus 30 is 80, it is balanced. So, now the change in length is equal to PL by A of the upper prismatic portion plus PL by A of lower tapering bar, tapering circular bar. The force acting on the upper bar is 30 into 10 cube, convert into Newton. Length is 1 meter is given, convert into mm. All forces you convert into Newton, all distances you convert into mm, so that we will get the change in length in mm directly. And we are converting area, we need to substitute area in mm square, Young's modulus in Newton per mm square. So, what is cross sectional area of the upper part? Pi by 4 into 30 square. Young's modulus is 200 into 10 cube. As the force is positive, plus 30 into 10 cube I have taken. This is for the first part. For the second part, as it is tapering member, it is having compressive force. So, 80 kilonewton compressive force, take minus 80 into 10 cube Newton. Length of the lower part is also 1000. Length of the lower part is also 1000, but it is a tapering section from 30 mm to 10 mm. So, here pi by 4 changing from 30 to 10. And Young's modulus you substitute in Newton per mm square. One common point you need to remember here is, be careful to see the consistency in units. All forces I am converting into Newton and substituting, all distances I am converting into millimeter units and substituting, so that you get consistency in the units. Tension I am taking positive, compression I am taking negative. Next another important point you need to remember is, you need to consider the data perfectly. Whatever data is given, you need to transfer it perfectly and then simplify. Say for example, the data here is 30, by mistake if you take it as 80, it is gone. So, substitution of the data in appropriate way is very important for us. Be careful about that point. So, what is the final change in length? 1.48 mm. So, is it plus 1.48 or minus 1.48? If it is plus 1.48, it is elongation. Minus, if it is minus 1.48, it is nothing but contraction. Contraction of the bar. Okay. Like this we need to solve the questions. We will move to the elastic constants. There are 4 elastic constants coming into the picture for homogeneous and isotropic material. We will consider homogeneous and isotropic material. Young's modulus is the major elastic constant, rigidity modulus, bulk modulus and Poisson's ratio. These are the 4 elastic constants we have. Young's modulus is normal stress upon normal strain. Rigidity modulus is shear stress upon shear strain. Bulk modulus is volumetric stress upon volumetric strain. Volumetric stress is nothing but normal stress acting all around the volume. Poisson's ratio is lateral strain to longitudinal strain. Lateral to longitudinal strain. The strain in the direction of applied force is longitudinal. The strain perpendicular to the direction of applied force is lateral strain. So, the relation between the 4 elastic constants are very important. You need to by heart. E is equal to 2g into 1 plus mu. E is equal to 3k into 1 minus 2 mu. E is equal to 9 kg by 3k plus g. Mu can be taken equal to 3k minus 2g by 6k plus 2g only. 3k minus 2g, 2g only, it is not 5g. 3k minus 2g, old system 2g BSNL divided by 6k plus 2g. 3k minus 2g, 3 into 2 is 6k plus 2g. Somewhere other you need to remember these cases. 9 kg by 3 kg. 9 kg by 3k plus g. By heart this 4 relations. Very, very important for solving the problems. Okay. Whether it is mechanical or civil, you need to by heart these elastic constants. Next is there is generalized Hooke's law. The Hooke's law, original Hooke's law is valid for uniaxial stress system only. If the forces are acting in one direction, we can use stress in the direction of applied force and strain in the direction of applied force. Both are proportional to each other. Stress proportional to strain. To make it equal, we use a proportionality constant called Young's modulus. So, generalized Hooke's law is valid for 3D state of stress. This generalized Hooke's law is useful for a 3-dimensional block or 3-dimensional members like this. Subjected to stresses in all the 3 directions, assume that all the stresses are tensile. If stress is compressive, we need to use minus sigma x, in y direction sigma y. Z direction we will get sigma z. So, our sign convention is positive is tensile stress. If you have compressive stress, use minus. And the dimension of the block is in x direction the dimension is Lx, in y direction dimension is Ly, z direction dimension is Lz. We will consider x, y perpendicular to the board z. So, the strain in x direction is given by sigma x by E minus mu times sigma y by E minus mu times sigma z by E. In the considered direction, directly the stress in that particular direction by Young's modulus. The other 2 directions are with minus and mu. And here sigma x, sigma y, sigma z, we have considered them as tensile. If compressive is there, directly here you need to substitute minus. Similarly, epsilon y, epsilon z are also taken. This is generalized Hooke's law, important for 3D stress system. Epsilon z is sigma z by E minus mu times sigma x by E minus mu times sigma y by E. Actually, epsilon x is nothing but the change in dimension along the x direction by original directional change. And this is delta Ly by Ly. This is delta Lz upon original length Lz. And if you want a volumetric strain of the member, nothing but delta V by original volume, nothing but sum of all epsilon x, epsilon y, epsilon z. All must be summed up together. It can be equal to sigma x, sigma y, sigma z by E 1 minus 2 mu. If you sum up all the parameters together, epsilon x, epsilon y, epsilon z, nothing but all sigma parameters you take it as separate and then add them together. Sigma x parameters are here, this is sigma x by E, and here it is minus mu times sigma x by E and minus mu times sigma x by E. So, here 1 minus 2 mu will come into the picture, 1 minus 2 mu into sigma x by E, like that 1 minus 2 mu into sigma y by E, 1 minus 2 mu into sigma z by E. If you take them together, sigma x plus sigma y plus sigma z by E into 1 minus 2 mu is the volumetric change. This is the point you need to remember, important for us to by heart. Like this you need to by heart. Mu is the Poisson's ratio, which is having mu is the Poisson's ratio. For engineering material, the range of Poisson's ratio is 0 to 0.5, that you know. Mu is Poisson's ratio, lateral strain by longitudinal strain. For engineering material, mu is ranging from 0 to 0.5. 0 is for cork, 0.5 is for incompressible material. Incompressible material means whose volumetric change is 0. Incompressible material we also call it as non-dilatant material, whose volume will not change. The ideal fluids will have Poisson's ratio 0.5. Ideal fluid is incompressible actually. Ideal fluid you might have come across in fluid mechanics, it is incompressible, not having viscosity, not having surface tension, and density remains constant. As density is constant, change in volume is 0. So, in that case mu is 0.5. If you consider incompressible material, mu is 0.5, then 1 minus 2 into 0.5 becomes, this is 0, 1 minus 2 into 0.5 is 0, so delta V becomes 0. Sigma x, sigma y, sigma z cannot be 0, but if mu is 0.5, this parameter becomes 0, so change in volume is 0. So, the point to remember is, for incompressible material, mu is 0.5, the change in volume is 0. Incompressible or non-dilatant material, try to remember this point for objectives directly. For incompressible material, delta V is 0, mu becomes 0.5. What are the examples of incompressible fluids? Perfect incompressible is not available, but nearly incompressible are rubber, clay, some kind of wax like paraffin wax. These are all highly incompressible. Water also incompressible. Now, if you take independent elastic constants for homogeneous and isotropic material are 2. Generally, these are Young's modulus and Poisson's ratio. If you know Young's modulus and Poisson's ratio from the relation, from these relations, if you know E and Poisson's ratio, you can calculate G. If you know E and Poisson's ratio, you can calculate K. All the elastic constants you can calculate it by knowing the two values. So, independent parameters are E and mu.